This video covers part 2 of section 1.3, Logical Implication. We're going to start by taking a closer look at the conditional. According to how the conditional connective was defined, a statement P implies Q is true when P is true and Q is true, and false when P is true and Q is false. These two truth values for P implies Q seem to make sense according to how the conditional is used in ordinary conversation. For the other two possible choices of truth values for P and Q, we said that P implies Q is true when P is false and Q is true, and when P is false and Q is false. Why should we define P implies Q to be true in these two cases? One way to answer this question is to investigate what happens if we did define P implies Q to be false in one or the other or both of these cases. So for our example, using the standard definition of the conditional connective, the statement form modus ponens, which is P implies Q and P, quantity implies Q, is a tautology. This statement represents a commonly used argument in both logic and ordinary conversation, so we want this to be a tautology. If we know P implies Q is true and P is true, then we expect Q to be true. This follows from the fact that modus ponens is a tautology. Let's see what happens with this statement if we use a different definition for the conditional. Suppose, for instance, we had defined the conditional by the alternative but incorrect truth table shown. In this table, we've defined false implies false to be false instead of its correct value of true. Is modus ponens, namely P implies Q and P, quantity implies Q, still a tautology with this alternative definition? We can answer this question by constructing a truth table for modus ponens using the alternative definition. Keep in mind, we need to use the alternative truth table for each instance of the conditional in P implies Q and P, quantity implies Q, when constructing its truth table. So we'll set up our table as shown and fill in the columns one at a time. Note that false implies false is false for our alternative definition. So in the second and fourth rows of the table, we have P implies Q and P implies Q turns out to be false implies false, which is false. We then see that with this alternative definition, modus ponens is not a tautology and hence not an implication. Since we want modus ponens to be an implication, it follows that this alternative is not a good choice for the definition of the conditional. The above truth table is just one of the alternative ways we could have defined the conditional. We could also try defining the conditional using either of the alternative, but again, incorrect truth tables shown. In the table for our second version of implies, we define false implies true to be false, but we leave false implies false to be true. And in the table for the third version of implies, we define both false implies true to be false and false implies false to be false. For both of these alternative definitions as well, we can show that modus ponens is not an implication. This means that the way in which the conditional has been defined is really the only possible way it could be defined so that it corresponds to our intuition. Remember that all three of these alternative definitions are incorrect. Alternative, in this case, does not mean you can use them as an alternative to the correct definition. Next, we want to look at arguments and fallacies. We've seen in the case that P implies Q is an implication. If we know P is true, then we can conclude that Q is also true. What happens if P implies Q is not an implication? That is, P implies Q is not a tautology. For instance, it's easy to check that P implies Q and Q, quantity implies P, is not a tautology. When P is false and Q is true, then this is false implies true and true, quantity implies false, as shown, which works out to true and true implies false, which simplifies to true implies false, which equals false. In this case, knowing that P implies Q and Q are both true does not enable us to conclude that P is true. The statement P may still be true, but we are not able to conclude that it is true with what we know. Using P implies Q and Q to conclude that P is true is called the fallacy of affirming the consequent, or more simply, the converse error. So now we want to define what we mean by an argument and a fallacy formally. Suppose P1, P2, down to P sub n, and Q are compound statement forms. A statement of the form quantity P1 and P2 and all the way down to P sub n implies Q is called an argument. The statements P1 through P sub n are the hypotheses, and Q is the conclusion of the argument. The argument is valid provided that it is a tautology, and hence an implication. A fallacy is an error in reasoning that results from applying an invalid argument. An argument is often written with each hypothesis and the conclusion on a separate line as follows. And in this case, for the conclusion, we have the symbol with the 3 dots, which means therefore. Given P1 and P2 and down to P sub n implies Q, we can think of it either as a statement form or as an argument. We only use the terms true and tautology or implication when referring to this as a statement form. We only use the term valid or invalid when referring to this as an argument. So for instance, it doesn't make sense to refer to an argument as being true, just as it doesn't make sense to refer to a statement form as being valid. For an example, the statement P implies Q and Q implies P is an argument. It consists of a conditional statement with hypotheses P implies Q and Q, and conclusion P. Since, as shown earlier, this is not a tautology, then this is an invalid argument. Now let n represent a particular fixed integer. We want to translate the following argument to symbolic form and determine whether or not it is valid. If n is divisible by 6, then n is divisible by 2. N is not divisible by 6. Therefore, n is not divisible by 2. So we have 2 hypotheses and our conclusion. To translate the argument to symbolic form, define the statement variables. P is n is divisible by 6. Q is n is divisible by 2. The argument then has symbolic form. P implies Q, not P, therefore not Q. Or if we write it on a single line, it looks like P implies Q and not P, quantity implies not Q. To determine whether or not this argument is valid, we need to determine whether or not the statement form is a tautology. We could determine this by constructing its truth table. Alternatively, note that in order for the statement to be false, the hypothesis must be true and the conclusion false. So the hypothesis, P implies Q and not P, is true, and the conclusion, not Q, is false. Now the first equality holds provided that P implies Q is true and not P is true. Then not P is true holds if and only if P is false. Also, not Q is false holds if and only if Q is true. So in order for the statement to be false, we need to have P to be false and Q to be true. Then when P is false and Q is true, the hypothesis, P implies Q and not P is true, and our conclusion, not Q is false. So these were the 2 conditions we needed in order for the statement form to be false. So this shows that we can satisfy these conditions, and therefore the statement is not a tautology, and hence this is an invalid argument. This means that knowing the two hypotheses, if n is divisible by 6, then n is divisible by 2, and n is not divisible by 6 are true, it does not allow us to conclude that the conclusion, therefore n is not divisible by 2, is true. The conclusion may be true, but we cannot conclude it is true from the hypotheses. For our next example, we want to show that the statement form P or Q and P implies R and Q implies R, quantity implies R, is a valid argument. This is a conditional statement whose hypothesis is a conjunction of P or Q, P implies R, Q implies R, so this is an argument. To show that this is a valid argument, we need to show that it is a tautology. We can show this by constructing its truth table. Alternatively, we can reason as in the last example. In order for the statement form to be false, the hypothesis must be true and the conclusion false. So that means P or Q and P implies R and Q implies R is true, and the conclusion R is false. The hypothesis is then true if and only if P or Q is true, and P implies R is true, and Q implies R is true. Then R is false, and P implies R is true, hold if and only if P is false. And Q implies R is true, holds if and only if Q is false. So now we have P must be false, Q must be false, and R must be false in order for the hypothesis to be true and the conclusion to be false. But then P is false and Q is false together imply that P or Q is false. And we said earlier that this had to be true. So this shows that we cannot satisfy all the conditions for the statement form to be false, meaning it must always be true, and hence is a tautology. Therefore, the argument is valid. So now let n represent a particular fixed integer. Suppose we know the following hypotheses are true. N is divisible by 6 or n is divisible by 10. If n is divisible by 6, then n is divisible by 2. If n is divisible by 10, then n is divisible by 2. Using the argument in the preceding example, what can we conclude must be true about n? So we'll first write these in symbolic form. Using our statement variables, P is n is divisible by 6, Q is n is divisible by 10, and R is n is divisible by 2. The hypotheses then have the symbolic form P or Q, and P implies R, and Q implies R. In the preceding example, we showed that P or Q and P implies R and Q implies R is a valid argument. So our three hypotheses match up with the hypotheses in this argument. So since this is a valid argument, whenever the hypothesis is true, then the conclusion must also be true. Since we're assuming the hypothesis is true, then the conclusion, R, must be true. Therefore, n is divisible by 2. So assuming the three hypotheses are true, we can conclude that n is divisible by 2.